Hello, my name is Rick Weibel, and the paper I chose is named SCAPHY, Detecting Modern ICS Attacks by Correlating Behaviors in SCADA and Physical. I believe the word SCAPHY is derived from SCADA, and if you choose to pronounce it SCADA or SCADA, I think that would affect how you would pronounce SCAPHY or SCAPHY. And then you see the last word there. Physical has a capital PHY. That is on purpose. We'll get into that. That's a backronym that the authors use. So that'll be explained soon. The authors are Ike, Fan, Sadowski, Valme, and Lee, and they all are affiliated with either Georgia Tech or Sandia National Laboratories. This paper was presented at the IEEE Symposium on Security and Privacy in 2023. That date, that year, is important. We're going to come back to that as well. That will shed some light on some of the content here. So let's talk about what we're going to go through. The first thing is we'll define the problem, which the authors say modern ICS attacks hide inside normal SCADA activity. Then we'll move on to the insight that can be summed up with the phrase right API but wrong phase, and we'll explain what that means. Then we'll talk about the solution. The solution is SCAPHY, and it consists of 3 pillars. And then finally, we'll talk about the results and how well it works and what the outcomes are. So the problem that the authors state is modern ICS attacks blend into normal operations. And so they use 2 real attacks that anchor the whole paper. In Destroyer, which took down part of the Ukrainian grid, and Oldsmar, that was the attack on the Florida water plant that nearly poisoned the water supply. You can see there's a big asterisk next to that. Again, I'll come back to that shortly. The key point in both cases is the malicious actions, assessing the OPC device objects in the Ukraine attack, and sending dosing commands at a water plant are things that a normal SCADA system does every day. So there's no obvious bad API to catch. Now back to that big asterisk, that is because the FBI later determined that there was no evidence that the Oldsmar facility was actually attacked. All the evidence points to an internal human error. This wasn't announced until the spring of 2023. And so at this point, or at that point rather, I'm guessing that the paper was already written since it was presented at the 2023 IEEE Symposium, which usually is in May. So more importantly than the Oldsmar event being an attack or not, is that an attack like this is feasible and a significant risk. Subsequently, I'll continue to mention this event and the risks if an attack like this happens. So why existing tools miss these attacks? So there's 3 families of existing tools, and each has a blind spot. The traffic and statistical analysis family, think passive network monitoring plus OT asset inventory plus protocol aware detections plus baselines. All that, you watch the network, you dissect the different protocols, and then you flag deviations from a learned norm. A lot of the solutions already in the market are based on this, and you can see I list a few there. There's Nozomi, Clarity, and also Palo Alto Networks, which is where I work, so they are getting a shout out. The next family is the sensor-based physical models, which basically means a level 0 monitoring of electrical signals directly from sensors and actuators. I was able to find one company that does this. It's listed there as SIGA. There may be others, but I didn't dig further than what I was able to find. And then the last family is process-aware tools. So you see the PASAD acronym there. That stands for Process-Aware Stealthy Attack Detection. And it is an AI ML-based framework that focuses strictly on process values rather than network traffic. It creates a baseline of things like pressure, temperature, and flow rate values, and looks for deviations from those as a possible attack. The underlying critique and the gap that SCAPHY fills is that each of these look at network or sensor data on its own with no connection to the SCADA execution content. And that context is the whole idea of this paper. So the core idea of the paper, again, is wrapped up in the phrase, right API, wrong phase. So think of it this way. The same API call can be totally benign or a red flag depending on which phase of SCADA execution it happens in. I'll define the phases in a moment. The slide here shows an example from InDestroyer. Its setup style calls are normal at startup. So setting up ICS device objects, loading OPC libraries, etc. are normal for the initialization phase. But when those exact same calls were made mid-operation to do its attack in the process control phase, they are out of place. It was the same API, but now in the wrong phase, and that mismatch is the tell. The call isn't suspicious in isolation. It's suspicious because of when it ran. The next few slides unpack what these phases actually are. So, build step number 1, initialization. Every SCADA host begins with initialization, and this happens once, one time. It loads the ICS drivers, sets up device objects and services, etc. Think of it as booting the control environment. Remember, setup style calls belong here and only here. The second build step, after startup, the SCADA enters process control. This is the actual job of running the plant. Unlike initialization, this repeats continuously in cycles for as long as the plant runs. Process control then goes into 2 sub-phases. So build step number 3 is process monitoring. SCADA reads the current state of every element, updates memory and the operator's HMI screens, and repeatedly asks, does anything need to change? Its signature API here is read file. Think of it as reading the device state. The fourth build step, also within process control, is when a change is needed, SCADA switches to process altering. This is where it runs physical domain logic, like a PID loop, on a set point to compute a control variable that sends that signal to the physical process. Here, its signature API call is write file. This is where it writes a command out to a device. And then finally, the fifth build step is when everything is put together. So the goal is to monitor until a change is needed, alter to make it, then return to monitoring. This loop runs over and over and over and over. Because the cycle is so regular, SCAPHY can learn the small set of API calls that are legitimate in each phase, either the process monitoring or the process altering, and flag anything that doesn't fit. That's the entire detection premise of the paper. Remember this loop process now because we will come back to it. So the solution, let's talk about SCAPHY. SCAPHY has 3 parts. The physical model figures out what's physically disruptive. The physics constraints capture the legitimate per phase API calls from the physical model. And then the SCADA software stack, or S-cubed, is the layered model of how signals reach the hardware. I want to point out that the 3 aren't fully independent. They interlock. So pillar 1 actually feeds pillar 2. So think of it as like the physical model is what drives SCAPHY down the right code paths to learn the API constraints in the first phase. And pillar 3 is a vantage point from where you're able to observe both pillars 1 and 2. It's the where do we tap into this layer. I'll give 1 slide each to the first 2 pillars, then spend some real time on S-cubed because as a framework, I think it outlives this specific system and has broader application. So the physical model, this is pillar number 1. This pillar asks the question, how disruptive is this command physically? And underneath that, SCAPHY parses the plant's OPC data to find the ICS elements, figures out which processes exist, maps how each element depends on each other, and then scores each element's state in a score of 0 to 1 by how much they move the process output. I'm not going to go through all the impact coefficient math. A good chunk of the paper was devoted to it though. But the data structure at the heart of this pillar is the PDIG. It's the process dependency and impact graph. The PDIG is a pre-process map that knows what elements exist, how they depend on each other, and what their relative order is, and how disruptive each one is. What this pillar catches is physical nonsense. So a command that drives the process somewhere physically impossible or past its safe range. So if it's physically impossible, think the inconsistent state for the in-destroyer attack, or past its safe range, think of in the water plane attack, something being set outside the set point. This is the pillar that understands how the plant works. The second pillar is physics. So physics is an acronym standing for Physical World Impact Call Specialization. Instead of a human writing rules, SCAPHY runs the legitimate program and records what APIs each phase uses. That recorded set is the rulebook. It's a baseline. So for each process control phase, there's a small specific set of API calls that legitimate SCADA makes. SCAPHY learns this set by running the benign SCADA program and driving it down its process control paths, making it react to element state changes so the relevant logic executes. Then it records which APIs fire in which phase. That recorded set becomes the definition of legitimate behavior. The key word here is specialization. Out of the huge space of APIs a program could call, only a limited specialized subset is legitimate for controlling the physical world in a given phase. Everything outside that subset is suspect. An attacker breaks the constraints in two ways: injection, which is a call that doesn't belong in this phase, or bypass, which is going straight to the hardware with no proper call at all. The bypass case is where the third pillar, S cubed, becomes essential, which is where we go now. So this is the pillar I find the most interesting. The Purdue reference model, which is the standard way we layer ICS networks and segment them, collapses the entire control system tier into one level 2 box. This paper argues for more granularity. Getting a signal from a SCADA program down to physical hardware passes through several distinct software and kernel sublayers. So S cubed breaks layer level 2 into 5 distinct sublevels, which is what makes them useful for detection. Let's build the stack one layer at a time over the next few slides. So at the top, we have layer S4. This is the SCADA application, the process control program from the phase section, which is its monitoring and altering subphases that I told you to remember for later. It does not touch the hardware directly. It works through the layers below. Layer S3, this is to reach a device. The SCADA program calls ICS callback functions that were registered when the driver loaded. These invoke the create file API call, which returns a handle to the device. This is the doorway from application code toward hardware. The next layer down, S2, the create file call hands back a device object, for example, a software handle like a COM port, and the OS uses it to mediate access. The read file and write file calls against these handles are the monitoring altering fingerprints from the phase section. Again, think of SCADA application loop. This layer is central to detection. Then there's layer S1. This sits below the handle and actually contains the ICS device drivers. So these run inside the Windows kernel through the driver model. They translate handle operations into real hardware access, which is on layer S0, the bottom. This is the physical I/O. The actual signal on the wire to breakers, valves, pumps, actuators, etc. So the full picture is a legitimate command travels starting at S4 down to S3, S2, S1, finally to S0, leaving a traceable API trail at each step. Traceable is the key word because it's the whole detection trick, and it's in the next slide. This is where Pillar 3 stops being a taxonomy. The stack isn't just a description of how SCADA works, it's a detection mechanism. The key concept here is provenance. Every legitimate signal leaves a traceable trail down the layers, so any command at the bottom can be asked, did you come down the stack properly, or did you appear from nowhere? This is the payoff for building the stack. The two attack use cases are injection and bypass. For injection, an attacker runs an API that doesn't belong at a given layer for the current phase. This is caught by the physics constraints, where traditional host defenses whitelist trusted programs, so if a malicious code executes inside an approved SCADA process, the whitelist waves it through. SCAPHY doesn't care which program made the call. It cares that the call is out of set for the phase. So injection into a trusted program still surfaces. For bypass, this is the one that needs the stack. For example, a rootkit skips the upper layers entirely and drives the hardware directly. The paper uses the concrete example of a raw device I/O control kernel call straight to S0, the bottom I/O layer. There's no offending API up in the SCADA layers to catch because the attacker never used them. So SCAPHY inverts the question. It sees a signal arrive at the physical interface, S0, and checks for the matching S2 activity that should have produced it. When none exists, it has no provenance. It knows it was sent around the proper path. Picture it this way. A signal shows up at the bottom of the stack with no footprints on the stairs above it. That absence is the detection. This only means something because the stack defines what the proper footprints look like. Even a sophisticated direct kernel object manipulation, a DKOM, rootkit that fakes the API call still has to physically attach to the device stack to function, and that attach step is an S-cubed event you can monitor. Specifically, it watches for a second attach to a device stack that already has a legitimate driver. The attacker is forced onto the stack's own terms. So this is the summary that puts everything together. There's two families, path and effect. The path family, which is where physics violations like injection and bypass come from the API trail through S-cubed. The effect family, these are physical anomalies, think inconsistent state and outside the set point, come from the physical model. Add in the signal level sanity checks that fall out of the DPIG's ordering that are missing, extraneous, or out of order. The distinctive thing is SCAPHY correlates a wrong phase API call with a physical effect and raises them as one alert. That's the difference from the existing tools in the market, which each produced one signal in isolation. So let's look back at the in-destroyer use case to tie the pillars together. First, the attack created a physics injection violation. It made setup style calls. It did load library, OPC browse, new device handles, and it pulled those during the process altering phase, which was the wrong phase. Setup style calls can only be made during the initialization phase. Second, there was a physical inconsistent state anomaly. In-destroyer opened a breaker while load lines were still connected. This is a physical contradiction. This event scored high in the SCAPHY analysis because the breaker's impact was 65% based on their model. Both of these fired in under 9 seconds during testing, and that proves that the right API wrong phase idea plus the physical model work together. So how well does it work? Well, let's look at these numbers. The top line numbers here are pretty strong. 95% accuracy. That's a big number, but we'll come back to this. 3.5% false positive. Also impressive, and we'll pick this apart a little bit as well. Under 9 seconds time to detect versus minutes for sensor tools. This makes sense because the sensor tools need time to establish baseline behavior. And then 2 dozen ICS scenarios in 4 industries. Cool. All right, but I want to be honest about the comparison. So the paper states a 95% detection rate versus 0% detection rate for existing tools. This framing is technically true, but pretty much unfair. The other tools get 0 on the SCADA attacks by definition because they don't look at SCADA at all. The strongest comparison is physical anomaly detection. So SCAPHY gets 21 true positives with 14 false positives versus the sensors models with 19 and 37. There is a comparable catch rate, 21 to 19, between the SCAPHY and the sensor model, but the real improvement is having less than half of the false alarms. That's the honest win, and it's still a good one for this research. So let's talk about some limitations here. So there are 4 main limitations pointed out. Number one, state switching is emulated, not live. They say they did this for safety, but fidelity is a risk. So live environments are crucial for real-world evaluation. A moderate step to solve this would have been to put this tool in an advanced lab environment with real devices. Number two, the analog signals are quantized to 3 broad levels, which cost some precision. The paper calls this out as a deliberate trade-off, not an oversight. So quantizing to these 3 limits impacts the score, which saves space, i.e. fewer states per element, fewer simulations, less memory, faster analysis. Number 3, the hypervisor is assumed trusted. A hypervisor level rootkit that escapes the VM beats SCAPHY, which they demonstrate in the paper. And finally, number 4, the rootkit defense leans on Windows KPP, which they admit could erode. It is worth crediting that the paper states these itself. So to close, SCAPHY is a strong detection system. It solves the blend-in problem by correlating a wrong phase API call with a real physical effect, and the numbers back it up. But if you ask me what survives this paper, it's the S-cubed model. SCAPHY is one system. S-cubed is a reference framework anyone analyzing SCADA hosts could build on, and the authors explicitly hope AV vendors will. That's the idea I'd like to stick. Thanks.